Good morning, everyone. Welcome to the Dig Deeper webinars. My name is Agnes Samper, and I'm delighted to be welcoming Professor Sarah Harmer today from Flinders University. I would like to remind you that this webinar is recorded, which means that from Monday on, you will be able to find the replay in the CRC Time website in the section News and Events. Also, I would like to remind you that you can type your little questions during the webinar because we'll have a Q&A session after Sarah's presentation. Sarah Harmer is a professor of applied physics at Flinders University. She's the founding director of the Flinders Microscopy and Microanalysis Department and the deputy director of the Flinders Institute for Nanoscale Science and Technology. Professor Sarah Harmer is also the project leader for the CRC Time Acid and Mine Drainage project that started last year and will last 4 more years. So today, Sarah will be talking about improved prediction, remediation, and closure of acid and neutral metalliferous drainage sites by examination of mine waste behavior at the mesoscale. Before Sarah starts, I would like to do an acknowledgement of country. So I would like to acknowledge the traditional custodians across all the lands on which we live and work. And I would like to pay my respects to elders, both past and present. I am currently in Brisbane, so I would like to acknowledge the Turrbal and the Yagera people. Now, Sarah, I think it's your time now. So over to you.
Thank you, Agnes. Okay, so today I want to tell you basically an outline of our project. So as Agnes mentioned, we've been running for approximately a year now. This project came together from a group of mining companies that we're working with, and also Roger Smart and Professor Roger Smart and Professor Andrea Gerson at Blue Minerals Consultancy. As many of you may well know, acid mine drainage or neutral metaferrous drainage remains a very vexed and costly environmental management problem for the mining industry, with costs varying in Australia alone from around 40,000 to 100,000 per hectare in remediation costs. So we believe that there is an opportunity to try and improve our ability to both predict the acid generation of waste and also potential remediation strategies for AMD and NMD on sites. And recently, through one of the foundational projects with CRC Time, which was led by Professor Caroline Holdham from Western Australia, she found that there were quite strategic opportunities that needed to be met as far as remediation for mine closure, communications and educations around the risks of AMD, and the governance and mine planning. So this project came together from that in terms of our objective is to improve both prediction of acid mine drainage of waste, the remediation of AMD and NMD, and provide, and this has really been provided through CRC, enabling us to look at mine wastes that come from extremely different climatic ranges and zones across the world, and also different evolutionary stages of the mines. So we have mines that are just opening, and we've also got historic legacy mines as well. And we range across climatic zones that go from -40 to +40 degrees Celsius. So quite an extreme range there. And it's provided us with a network of industry partners and also regulatory bodies as well that are providing support for us in the project outcomes. So the project overall has 5 different phases associated with it. And one of the overall objectives of the project was really to bridge the gap between what we saw as lab scale studies from kinetic leach columns of potentially 2 up to 20 kilograms into the mesoscale range. So we're looking at up to 2-ton experiments in this case, so that we can try and understand the differences between experiments that we've done in the lab versus what we see in site. And to be able to have accurate forecasting and control of AMD, we believe that one of the main concerns there are climate, geochemistry, and microbiology that are playing key roles. So we are assessing each of these during these phases. In the first phase, we're taking our untreated waste from each of the mine sites and developing strategies for those individual mine sites in terms of whether we're doing kinetic leach testing, mesoscale testing, microbiological testing. We're doing full mineralogical analyses of each of these. And then moving on into phase 2. In phase 2A, we're doing our geochemistry as far as quantitative X-ray diffraction, also MLA and QEM-scan as required, or ICP, laser ICP-MS. In phase 2B, we've set up our kinetic leach columns in order and done our basic first acid generation tests and selecting standard remediation strategies that we will apply in the later phases. Scaling up some of our sites in phase 3 and applying some of those remediation strategies. In phase 3A and going into phase 4, we're really doing a feedback or a loop in which we're going back and looking at all of the characterization methods that we have used and reevaluating them to see if they have efficiently identified what the acid generation would be and what remediation would be before moving on into the next phase of remediation testing, and then down into phase 5 where we look at information dissemination and training sides. So if we look a little bit more, I guess that was a general overview. Phase 1 in particular is setting up our monitored or baseline studies. So we have 10 different sites with this project, ranging from as north as Alaska and Mongolia, and then throughout parts of Australia and the US. Each of our companies, we've worked individually with them to design experiments that suit their particular waste and conditions. We have 2 different tailings and the other 8 samples are of waste rock. And so our experiments have been set up according to each of those parameters. We have set up our IBCs, you can see on the picture on the right here. These are our large IBC containers that carry up to 1 to 2 ton experiments. They are set up so that we can have oxygen sensing, moisture sensing, pH, and electrical conductivity throughout the tank in 3 different levels. We then have a drainage mat where solution can flow through without losing any of our waste rock, and then out through a plumbing for collection for water analysis. We've designed sprinkler systems that sit on the top so we can simulate rainfall, which is according to the particular climate that we're dealing with. And in some cases, we're dealing with only sort of a few tens of centimetres of rain per year. Others, we're talking metres of rain per year. So quite a range of climatic zones there. The outcomes of this phase are to determine the leach mechanisms and rates of acid mine drainage from each of these wastes, and also to do some biogeochemical modelling of the wastewater and flow. Each of our sites, we're setting up sampling for microbial populations, and we've developed our own sampling methods for both the mineralogy and microbial sites. Our strategy, thereby in the way that we've set up these experiments, is for remediation is to exploit local sources of neutralisation capacity. One of our overall gains is to work with local EPA sites in order to, and governing bodies, to work on management of sites to be more specific to the individual mine site, and to be able to make strategies around using those local sources for acid neutralisation. So some of our sites have a lot of carbonaceous material nearby that can be used. Others, we're looking into different plant life or also capping technologies or chemical methods. And in the lab, we'll be looking at some biological methods as well. So in phase 2, we're doing all of our basic characterisation of the material. We're looking into both the mineralogical and the microbial life that exists on the mine site. So our biological sampling on each of the mine sites is being carried out in a strategic manner. Everything's performed in triplicate and sealed and filtered on site, so that we can then extract both DNA and RNA from the samples. We're using full shotgun sequencing so that we collect not just the bacteria that are present, but also fungi and viruses, to make sure that we get the full genome of what is available. We have bioinformaticians who are working with us on the project that are developing methods that are also specific to looking at mine waste, and having a variety from both tailings as well as rock. It's the procedures for detecting microbial life are significantly different. Traditional methods, you can easily extract microbial life from filtering through water, but on some of our drier sites, we are working with some experts on collecting microbial DNA off of rocks. So we've had three of our sites so far have had microbial life examined, and another 2 are happening in the next couple of months. So we've been able to detect some quite low quantities of DNA and sequence them. We're hoping to get with the RNA profile as well, is not just identifying what is present, but also what its function is, which may vary, of course, over the life of the mine and as a function of climate as well. So we really want to investigate the possibility of using them as both sensors of what geochemistry is, biogeochemistry is occurring. We're doing a full characterisation as far as our geochemistry, as well as high resolution mineralogy of each of our sites, and using those as a basis along the line with our chemical toolkit from the Amira handbook for assessing the mine waste. In phase 2B, so this is between 6 and 24 months, we have several sites that have chosen kinetic leach testing. In this case, they are a bit larger than the traditional Amira funnels. We've decided to do longer columns and scale up to 5 to 10 kilograms in size, rather than the 2 kilograms that we see in Amira funnels. We have both EH, pH, oxygen and moisture sensors in each of our columns, and also drainage that comes out at the bottom for us to collect the water samples. All of them are kept at a controlled temperature and at different saturation levels. Some of ours are being spiked in some cases with different microbes in order for us to understand the effect that they would have on the system. But it gives us a really rapid or faster idea as far as what the acid generation capacity is of those wastes in comparison to our 1 to 2 scale experiments. So far, we've set up our IBCs, or larger scale experiments, for 2 of our companies. As you can see, these are both 1.2 and 1.6 tonne from left and one on the right. Each of them has the oxygen sensors, EH measurements, as well as moisture and conductivity, so we can, and it has piping at the bottom. They sit on top of tubs which have weigh bars on them, so we can measure their weight in real time, which is sent to a data logger. Our outdoor site at Flinders is just finished construction, so we have a compacted base and all of the power supply that's just been set up this week, actually, and we'll be moving these IBCs out and connecting the sprinkler systems to them next week, hopefully. So the advantage of testing at a meso-scale is the possibility to have these larger scale kinetic tests that are a little bit more representative of what we would see on site. So we are not heating them. They will be at the weather that they are exposed to in Adelaide, which is Mediterranean, quite on the warmer side. But again, they'll be covered and have a controlled amount of water, which we can measure with the weigh bars. We will, after we have our initial testing, as far as setting the experiments up and getting an idea of the acid generation through these kinetic tests, we will move on to some larger scale remediation studies in these IBCs as well. We have one partner who's setting up an IBC on site for us as well. It's MMG in Tasmania, where we will start to do some remediation experiments from local plant life, as well as carbonaceous sources that are near the mine as well. Sometimes this is quite difficult to do on a mine site because of the amount of work and monitoring them and changing of staff, but we're very fortunate that they're committed to help us with this. So from phase 3, we really want to ensure we've identified all of the microbial markers in terms of what microbial life exists and what their function are. We're developing new protocols as far as our shotgun sequencing and also the bioinformatics processing of the data. We hope to be able to identify all of the biogeochemical processes that are occurring and assisting with the acid release when we combine it with our mineralogy, and then work on some controls for those. We will be tracking the microbial communities where we can to try and see the change as far as different times of the year with climate, for moisture levels, and also our pH. We're going to try and exploit our local neutralising waste rocks from each site, which they'll also send to us, or we have, as I mentioned, one company so far, but we hope to have a second company who will do some experiments on site as well. And the outcomes of it will all be looking at expressing those to local communities, and we'll be writing a new handbook, which I'll talk about in a minute. So phase 4 is all about us going back and assessing and looking at what we've done so far. So other than sending out our beautiful PhD student, Alex Hayes, that's pictured there for hard labour out in the tailings, we will be looking at all of our sampling methods, particularly with the microbiological testing as well, and sampling methods and how we can become more accurate in those, and also the timing of when we undertake those measurements, and constantly assessing what tools that we use for the analysis. We'll go back and refine as well on whether what type of samples can be sufficiently analysed using quantitative XRD, MLA, QuenScan, or where do we have to go further and look at trace elements with laser ablation ICP-MS, for example, or imaging XRF. So we'll be looking at improving some of those strategies as far as our neutralising capacity. So we've been looking particularly at individual carbonate systems in what their effectiveness on neutralisation is, and also part of our silicates as well, to whether they are acid generating or when they are ion containing or not. And also going back through some of the Amira handbook chemical analysis, so looking at sequential extraction methods and changing and altering those. We've extended one of them that they're doing at the moment in a longer method to try and individually extract minerals one at a time, and to see if we get a more accurate picture of our acid generation and reactions over time. Particularly when we have a lot of stored acidity, potentially if the site has a lot of jarosite, which again could be an indication of microbial life. And we'll be comparing, so we've got 2 sites that are tailings and 8 that are waste rock. So that particle size is extremely different, from a few microns up to 10 centimetres approximately in diameter for our IBC experiments. In this process, we need to recognise the risks and opportunities with this. So we'll be looking at measuring effects of nitrate in solution and sulfide reaction rates, and also silicosis or any other hazards. And all of this testing regimes will be fed back to our partners in a waste and into what will be replacing the Amira handbook with a CRC time test handbook, which will outline not only just the chemical methodologies that we're been using, which is what the Amira handbook was, but all of our microbial testing as well will be added to the handbook. So just to give you a little bit of insight, one of our first studies that we've been looked at, which is with Tech at the Pollara mine site. It's a legacy site. It was decommissioned from 2008 to 2010. And at that time, we want to establish the geochemical and microbial processes that are at that site at the moment, because they have a natural attenuation of metaferrilous drainage from their emission point out into their pastoral dam. So this is an example model of where they have rainfall moving down through. They also have groundwater out to their dam. So the first aim was to find out the geochemical origins of lead, cadmium, and zinc that they can see in their groundwater, and identify reactions that may have released these elements into the mine water, and identify any biogeochemical influences that may have assisted this. We took samples from, this is the Northern Vent Rise 1, which is an image on the left here, in triplicate at each sampling site as we go down through to the pastoralist dam. So we have quite a number of samples, over 90, I believe, going all the way down to the dam. We also had core samples, which were legacy samples from the site, and we took XRF on site of those, and also bring sampling of them back to Flinders for quantitative XRD. So far, the mineralogy indicates that the sulfide minerals are marcasite and galena and sphalerite. Of course, galena and sphalerite are not acid forming, but marcasite has some potential. Overall, the waste isn't greatly acid generation. So there's neutralising carbonate present in the form of calcite and magnesite. There is some cadmium and some thallium and potentially small amounts of arsenic that we couldn't locate in the core samples using SEM, QXRD or XRF. So we will be doing some laser ablation ICP-MS and also some XFM at the Australian synchrotron to see if we can find the root of those elements. The water samples, solutions were taken along the path from the 8 different sites. And we find that the zinc concentrations were high in the first couple of sites, so out of the event horizon, but further down to the pasture stand that they were quite low in that respect. The pH ranged from 1 to 8 along that line of measuring, and the zinc concentrations we believe are decreasing due to secondary mineralisation. So the EH or electric and EC measurement that we took along that site and the sulfate increase from calcium, sodium, chlorine, potassium and magnesium. They were quite correlated on those measurements, and we believe that we're expecting carbonate alkalinity decreases that pH. We believe that because the salts are sort of basically evaporating, leaving those elements there, we have on a student who's working on the microbial analysis at the moment. So she's been able to extract DNA from all of the samples and shotgun sequencing, and she's just doing the analysis and bioinformatics at the moment. And she sees quite a large range of both microbial funky life that are present on site, actually in the low pH range and high metalloid range, which is very interesting. I'm just trying to understand how that community changes along the track. Sediment samples that we took as well, we took both underwater as well as near the edges. We can see correlations of both arsenic and lead and sulfur, thallium and inorganic carbon with a small amount potentially calcium there. The quantitative mineralogy tells us that we've got various types of silicates, gypsum, marcasite and sphalerite. And RSEM showed us that we've definitely got microbial involvement there. So we've got some framboidal pyrite that's formed. And our quantitative mineralogy suggests that we've got some aragonite that's been formed and calcite in that process. So far we've completed mostly phase 1 of 9 out of 10 sites. So we're still waiting on samples from one site, which is a new mine, just opening. We've started kinetic leach tests for 6 out of 9 sort of companies at the moment. We expect to have about 40 leach columns going, kinetic leach columns in the end. So we're about halfway through those at the moment. All the quantitative XRD type mineralogical analysis has been done, but we'll be doing some more in-depth studies as we go along. We've developed all of our sampling methods for microbial and mineralogical testing and tested 3 different sites for microbial life, with another 2 happening in the next month. And we have a PhD student who's working on new methodologies for the bioinformatics processing of those. Remediation trials have started for one of our first sites, and that's been done in the lab, but we will start doing that at a larger scale in the next month with the IBCs. And we're in the process of updating the Amara handbook and turning it into the CRC handbook at the moment by adding all of our sampling methodologies and testing for microbial life. So by the end, hopefully, we will have some industry-friendly training models that we can talk with companies about in studying. So I need to thank very much. We have a wonderful steering committee, which I meet with quarterly, which is led by Paul Brown from Rio Tinto. We have John Crosby from MMG, Philip Fairs from DM in South Australia, Jeffrey Batt from Miro in WA, Susan Baldwin from Canada at UBC, and Ursula Salmon from in WA. So we thank very much our partners from MMG, Rio Tinto, BHP, FMG, Newmont Tech. The AGRF are also a part of our project, along with ACANES and of course our government departments and research facilities with mineralogy and WEA. Thank you very much for listening today.
Thank you very much, Sarah, for this very comprehensive presentation of your project. I see there are a few questions in the Q&A chat, but I will start with one. So basically, so I'm a geologist. So one part of your project is to do mineralogy characterization.
Yeah.
The other part is to do the microbial population identification. Yes.
Yes.
And the other part is to try to reunite everything.
Yes.
And try to provide tools to accurately try to tackle the acid formation or slowdown, and then put everything in a beautiful handbook. That's right.
Yes.
That's your project.
That's a summary. That's a very good summary.
So my question is, what is the most challenging part of this project? What is the most difficult part for you? What is, and maybe the most innovative part?
Yeah. So, yeah, and I guess that the challenges are different in each of the areas. So, as far as the mineralogy has been quite simple in the traditional methods. It's just moving outside of that when we have extremely low concentrations of trace elements. As far as microbial, there are a lot of challenges there from a fundamental and applied level, really. Sampling methodologies took quite a while to think about from each of those, and our sites are so diverse that there are sometimes very small windows for us to be able to collect samples. Like in Alaska, for example, we usually have like a 2-month window, and it's the only time that we can sample, which then, of course, it's like, well, we're only going to get an idea of what's happening at that time, necessarily over the whole life. And we know that despite the fact that it's so cold, here it's -40, -50, the ground isn't frozen deep underneath. And also due to heating, that some of the heaps are warmer inside as well. So for us to be able to get a really high quality and accurate picture of what's going on in the long term on that is challenging in that respect. And that's where we need to try and simulate still in the lab some of those conditions and what happens as a function of temperature and oxygen ingress, for example, with the microbial life. And there's a lot of microbial life that either we don't even know about, it's not in the libraries at all. And so trying to determine what they are and what they're doing, or what are the important ones to look at, because the shotgun analysis gives us a picture of everything. So really trying to close down and say what is important is a very crucial step in our analysis of the data. But
Thank you.
I mean, there's a lot of, it could go on forever, I think, in some of those areas. There's a lot of good science as well as things to discover.
So is it, like, just a last question, but for the trials in Australia, do you go sampling like along the year, like in different seasons?
Yes,
Yes.
so the local ones we will be able to sample, yes, throughout the seasons. It's just that there's a few ones that are quite remote or that we can't get on site. That will be difficult.
And with specific conditions here due to winter and microbial activity still happening.
Yeah.
Thank you. So we have questions from Steve. So I'm gonna read it. Are you also looking at fungi, microorganisms that are releasing chemical constituents from non-sulfides, such as phosphates, minerals like lithium phosphates in the lithium pegmatites or monazite? Many fungi target these minerals to access phosphorus and may release other chemical constituents as byproducts by concentrating on sulfuric waste. So are you missing the potential for NAF waste to release significant amounts of contaminants?
I think there's a couple of questions in there.
Yeah, there are more questions. Cool.
So we are doing also the analysis of all microorganisms to begin with, but bacteria to start with, and then we will go down and look at potentially what fungi will be doing. That potentially, as you mentioned, may help release chemical constituents from the non-sulfides. We don't have any lithium actually studies in our group of mines, so we haven't investigated that to date. But what you mentioned is interesting, is that phosphate will be of particular interest. So we will be having a look at those, and my colleagues who are the microbiologists and bioinformaticians do work somewhat in that field. So they will, we will talk to them about doing that for sure.
More work to develop.
Yes, I on the microbial side, there is a lot of work to be done, really. It's at the beginning here. Absolutely.
So there's also a question about climate change. So would you be interested in climate change data? Well, I'm going to read the question. Okay. Also, an emerging issue that we may need to address with climate change is the effect of increased fire frequency and intensity on closed TSF and waste rock dumps. There's an emerging body of literature that indicates hexavalent chromium and arsenic can be released from ferruginous mine waste at high temperature. So more prospects for some work to do.
More prospects for work. Yeah, that wasn't part of our original study, but yeah, perhaps that could be something that's done afterwards. That's really interesting, actually.
And would be interested in having more like prediction on climate change on your trial sites. There would be more work to do, but would you that inform?
Absolutely. Yeah? I mean, absolutely. I think there's quite the function of just temperature and water essentially are two of the main functions as far as our main elements, as far as the acid generation and microbial life. So they're absolutely extremely important to us. Yeah, we have collected sort of the previous climate data from each of the sites, because this is how we're trying to simulate rainfall and things at each of them. But yes, I think that would be another added
another part of the project that could come.
But yeah, absolutely, it's important. Yeah. Yeah.
So then it's a comment. Thanks, Sarah. Very informative, and I look forward to continue working with you. So
yeah. All right,
excited colleague. Well, we still have time for more questions, but yeah, would you like to add something, Sarah?
No, just thank you for coming, everyone, and I'm more than happy to hear from any of you. You can email me at any time with questions, and we'll be happy to talk about it. And we, yeah, look forward to updating you later in the project when we have some more answers.
Thank you, Sarah. Yeah, we will invite you again to give a presentation. No worries. Thank you very much, everyone. And I think this is the end of our Dig Deeper webinar for today. And thanks again, and we'll come back next time. Thank you, Sarah.
Bye.